Thank you very much, Nathan, Carlili, and Antonio, to invite older men like me, okay? A new opportunity in my life. Of course, for more than 20 years, I tried to solve this problem. I didn't. But the idea, before I start, suppose I have in 2 dimensions, 4 points. 1 mile, 1 mile, 1 mile, 1 mile. 1 kilometer, what's what? 1 something, okay? And you give me some telecommunications cables, what to contact these people. This means I like to have, for each pair, a path, at least. The first thing people used to do, you construct a complete graph. They love it. Okay? 1, 1, 1, 1, square 2, square 2. And then they find a minimal spanning tree. For instance, this one. What value is 3? Okay, there's one there, of course. But somebody say, oh, but if I get this one, but this point here is much better. I put one vertex more. I can put another vertex. And if it's not the better solution, the best solution, one of the best, is something like this. All the angles is 120 degrees. Okay? And here is 1 plus. That's the best you can do. We used to call this Steiner problem in Euclidean Steiner problem, in a sense. Okay? Of course, have 2 solutions to dimension. This one or this one, the same one. Yeah? But how you arrive in this kind of solution? It's not intuitive. Then this idea is, I start now my talk, associating the history of we start with Fermat and so far. Okay. Perfect. That's the plan of my talk, okay? And we start. Suppose this problem is probably, I think so, is Fermat in the 17th century. He gives you a triangle in 2 dimensions, and you are looking for a point X in which distance between XA plus XC plus B has to be minimum. This first one problem, you know. And this problem you have 2 extensions. One is given P points in n dimensions, find a point in which distance between this point all the other points is minimum. We call the Weber or Fermat-Weber problem. The other one, you can use a number of points, not just one, to find a spanning tree which minimizes the total thing. This is Steiner or Fermat-Steiner 3 problems, Euclidean 3 problems. Okay. The problem because you don't know where is the point. In this case, of course, it was Torricelli proposed this solution. One solution is the construction. In this case, in this example, you find you construct it. You have 3 equilateral triangle here. You construct these circles. Intersection will be you just need 2, not 3. But okay, you can. All the angles will be 120 here. This intersection. But when one of the angles is greater or equal 120 degrees, this point goes to this one. And this, almost 200 years later, no? It was defined as exactly. In this case, no differentiable in the sense. Then this is, we call Fermat-Torricelli point, or Napoleon have some ideas about this point and so on. Okay? And as I said before, you have 2 kinds of expressions. One is the Fermat-Weber, and not Fermat-Steiner, just Steiner, Euclidean Steiner problem. Because in graphs, you have these Steiner 3 problems in graphs, okay? A different one. This one, I have to calculate the distance is Euclidean 1, 1. Okay. All right. Then let's try now in calculus 1, for instance, when you have you try to solve this problem, no? The first things you can try is, try point B, A, or C, and find something like that. But you can try to write the formulation, as I said there, no? You have minimized the distant total distance, okay, by the verts, and you have the gradient here equals 0, and you try to find the solution. Suppose it's differentiable, okay, have d, you have equals 0, and then again you have all you suppose all the determinant here. The determinant here is not 0. Then you can try to calculate to find the 0 of the gradient, and you find like I can show you, because this equilibrium in physics now has to be equal 0. Okay, the summation is equal 0. Then you can get these equations and so on, and you could get 120 degrees. It's not difficult, but you have to work. It's other idea how to solve this problem in this sense. But it's very nice to do. And like I prefer to show this kind of, I start with this because it's a different way. Okay, then I just show the same thing. I start here because I prefer to start with this figure, this illustration, than the 1 point, because it's not intuitive in this sense. Then, like I said before, you can try now to get something else. Let's try some definitions. Now I give you p points in d dimension, n dimensions. Find a tree that spans these points, the given points, use or not other points. That's the idea. People used to call this this problem is Steiner points. We say this problem in the solution. Big problem, they say the solution is Steiner problem. But normally you can, if a configuration you have this point, you can call the Steiner problem points in this sense too. Okay, but normally when you get the optimal solution, you get the Steiner points. But you use to say this is Steiner points for this topology. Right? You see what is in topology and so on. Okay, that's just the problem is NP hard. It's a nice demonstration. Okay, and these are Euclidean in this sense. Suppose some ideas, some solutions in 2 dimensions. Okay. Here you see 1, 2. Look at that. That's normally you call this as we have just 1 point here. If I give the 5 points here, just 1 point to the solution. I just need 1 point. Here for the pentagon, I need 3 points. Here for the hexagon, I had no points. All angles as 120 degrees. Okay, that's the kind of example you can find. Then you can have 0 points, 1 point, 2 points, and 2p minus 2. I have to show. Okay, it's you have more than p minus 2. You cannot form in the sense you cannot construct a tree. Then you can. It's not difficult to see. That's this kind of solution you can get one. Then, most of the people which work in these things, they have no model. They have an algorithm to enumerate, like Smith. For GeoSteiner in 2 dimensions, all the people from Australia and Denmark, they have the GeoSteiner, but just for 2 dimensions. I'm not interested in 2 dimensions, 3, 4, and so on. 2 dimensions, you can cut a lot of solution because you have the collisions of the point like that, you see? You have this kind of collision. Then you can eliminate this. In 3 dimensions, you cannot do that. It's very easy. Yeah? Yes. I will try to say about p minus 2. P is number of given point.
Oh, I see.
You know? More than p minus 2, you cannot form, as I said before, a tree.
So even if you knew how many points you want to add, the problem is hard.
That means you perhaps have 0 points, 1 point, till p minus 2. Okay? That's like, we can prove it. It's not difficult to prove it. Okay? And then you try to do something like that. Okay? Every space, in every dimensions. Here's some idea that's just, I put one is a tetrahedron, is a topology. In this case, topology is optimal. For the cube, the topology is not the optimum, but it's a possibility to have in 3 dimensions these things. Just to you see this kind of problem you have. Okay? Then, here for the icosahedron, the tetrahedron, but it's not the optimal solution. That's a solution. It's a possible solution how to contact these people. Okay? Then, like that's, I can try to see. The first property, given pinpoints, xi are d, 1 to less big points, the maximum number of Steiner points is p minus 2. Okay, it's not difficult to prove these things. We call non-degenerate Steiner point when you have the valence equal 3. Okay, in this case, you see before, one of them have no. You can sometimes when you don't have any Steiner problem, you can see the problem is degenerate. But it's kind of thing. And the other thing interesting. Sorry. When the edge in any dimension, the edge associated to a Steiner problem like this are in the same plane everywhere, because otherwise it's not minimal. That's good things to speak. That's geometry ideas for any dimension and so on. Okay. Then my idea is how to write the program, the linear or nonlinear interprogramming or something like that, differentiable, not differentiable, to try to solve this problem. Because of course, it's very nice to have a numerator, but for me, if I don't get a mathematical model, I'm not very sure. I cannot work and not calculate upper bound, a lower bound, and so on. Then some examples. Just some examples to see. Here this Steiner point, etc. Here, as you see before. Here, sometimes you have some different topologies. Just to see. The number of, that's nice, the number of total possibility of 0, 1, the k is number of the points, you see. You can have 1, 2, 3, 2p minus 2, okay, in this sense. That's total combination. I'm very interested now for the called full topology. This means I suppose I will have p minus 2. That's my opinion. When I start to construct my model, I suppose I shall use p minus 2. And then just for 10 points, look at that. You have 2,027,000 possibilities. That means the number of configuration, as you say. The first formulation we proposed in 2000, I think so. In 1994, but we published in 2000. Have two. The second depends on the first, but it's interesting. I will show you. The idea. Suppose now I give you, for 4 points, I give you this topology. It's a topology, just logical topology, not the final topology in the sense. That means how from here I have to minimize this kind of problems, non-differentiable, distant geometry, distant Euclidean distance, to find this one. That means from this configuration I get this solution. For another configuration, if I start with another configuration, for instance, like that, I can get another one like that. In this case, I have two solutions, two possible solutions. In 3 dimensions, I can have 3 different solutions. In this case, that's in this case because, but in this case, perhaps this one or the other one, I have to try to in 3 dimensions the 3 possibilities I have. For each one, you calculate this one. Okay, that's the idea. But this problem, of course, is strictly convex but not differentiable. For each configuration. Then how put all the things together? Then my idea how I construct a support graph in this sense, because for me, this point, for this point are not fixed. I have to find this position of the point. It's not given, my point. Like, that's the problems we have. I have how we call D the dimensions and the number of terminals, given terminals. Theta 1 to the end is the given terminals. X is the index of sets of Steiner points. P the terminals. Okay, P the given points. Okay, and so on. And we construct this kind of graph. It's much better to see how I construct it. And we suppose xk is in the dimensions, k points is in the x, and y uv 0, 1. If uv in solution, u 0, 1 is uv in solution, and so on. Because we have two kinds of arcs or edges. Okay. Suppose suppose we have n equals 6, please, and I try to start with 4 points. I have now to construct the 4 points. I don't know where they are, but I know the maximum point I need is 4. Okay, and I construct now in 4 points. I click with 4 points. Okay, and then for each given point, I have this kind of construction. You don't know where it is, but okay, you are, and so on. I construct my again. I have 6 points. I put p minus 2 points. I construct a k4, sorry, and then for each given point, I do that. Look, this is a possible solution of the problem, 0, 1. Okay, possible solution. Okay. Just this is possible topology, not the position, the topology, the logical topology. Okay, they have calculated point in 4 points. It's one of the ideas. I have a lot of them. Then just to see is that. Then I try because I say, but if I have no, for hexagon in the case I have no Steiner problem. My idea is okay. I try to say it for each. For each Steiner point, the valence is equal 3. But I can suppose there exists an edge with the distance 0. Why not? To try to represent the case we call degenerate. Okay. That's nice because how can you do? This model will be able to solve approximately, of course, because you see, it's continuous. Approximately for the hexagon, it will find the 5, equal 5, something like that, even. That means all the points will be degenerate. Okay. And then this is just a possible position of the edges. I don't know exactly. We have to calculate all this. For 10, you know, it's almost 2 million, something like that. So okay. Then I try to with the first example. I have to look. That's a big problem. We start with the variable 0, 1, just to see. Okay. Then I finish with 1. Variable 0, 1. Of course, from P is given point. Q is the index of the Steiner point. I don't know. Then I know just 1 from each vertex. I have just 1 working for me. Okay, just one for the other ones. Then I can write this one here. This one is not necessary. We can solve without this. It's kind of cut. I introduced for the. I know the Newton solution in B3, but it's nice to force this if it's 0, 1. It's kind of cut in a sense. But I put direct. And here, this cut is very interesting. Oh, sorry. The big problem, what's happened to TSP when the whole? The problem are subtours. The big problem is to solve this kind of problem, and you find subtours, subgraphs, not connected. And in this case, it's easy. Because I don't care about the position of the 4 points, with p minus point. We can change the points. Then I write these things here. I explain you how to, what is this. Look, for n equals 6, please. Then I have this, I fix 7, 8 equal 1. Okay, why not? I can fix one of them, I don't care. And then I have this kind of problem here. That means I have 6, the number of total spanning tree for 4 points is 16. Well, P n minus 2, okay? That's 16. In this case, I find 6. I have just 6. Then I keep the connected of the problems. It's very easy because in this case, this is very easy constraints because you can change the position, don't know. Then I can describe like that. But if you see, have just two types of trees. Because look at that. This one, that one is isomorphic. And this one, there's 4 and 2 here. That's if I could not find another. I could work just with the 2 here. Other one is isomorphic, but it's best I can do. I could not have another one. Okay, we try to write something like that, to some heuristic you can do, and so on and so on. Okay, but it's idea. Okay, but I'm sure the solution will be connected. Then, much better. Then it's nice. That's the 3 family of constants as I have seen in Y and Z. And this one is just for d greater or equal to 3. For 2 is not true. This means you have not more than 2 for 8. XP is the dimension 0, 1, 0, 1. And now, that's a big problem. I multiply for 0, 1 for a distance. That's mean. That's all the distance of my graph. But some of them I have to calculate because I don't know the position of x. Then I have to calculate this one. It's a square root. It's not differentiable, but and even the continuous relaxation is not even convex, and so on. That's the first formulation, and we in 2000 we found some. My idea is to like the paper written in 92 by Smith, his PhD student. He enumerates all the possibilities. Very nice way to enumerate and have two kind of branch. My idea is to find a model to get a good lower bound. That's my idea. Then it's very bad, this one. Okay, but I try to do something this way. That's in 94 and so on, like that. Okay. Questions about this model? I think this model is a good one. In the sense, it's complete. It's all right. That's okay. That's just to. Then we present this paper in 2000. Philippe, Maculan, Xavier, and myself. In 2000, but I wrote this in 94, 96, and so on. And my idea is actually, this paper is very interesting. If you have to know about Steiner problem, it's a very nice paper. A large one, almost 40 pages, and have a lot of ideas in 92, and so I work in this time in these papers, and I was dressing this paper and this one, okay? But have no model, just the complexity and so on, the space and so on. Claudio Ambrosio, Marcia Famp, and John Lee, and Vegas, they have some no ideas how to use some non-convex formulation and so on and so on. And my colleagues here, I see. Now, the nice things, because I'm working with the distance geometry, with the Euclidean distance, I can devise. That means I can get the given points. I'm sure the points, the Steiner point will be in the convex hull of the solution. Then I can find the larger distance, divide all by larger. Then I have the equal 1. And then I can, the big M has B equal 1 disappears. I have a big M equal 1. I don't see, but I have a big M there. Okay. Then the idea, and here is interesting. Because why I suppose that? This is okay. This is very important because I try to show you a different way to have a relaxation. I would try to find another economic functions, all the objective functions. My relaxation will be not change the constraints, but the objective functions, for which I can compute easily. Easy in this sense is differentiable, and so on and so on. Then this thing is very important for me to guarantee some kinds of I'm sure this will be less or equal, and even the possibility for each one I will present. And this space. We can do that because we are working with distant geometry, with Euclidean geometry. You can divide and so on. You can suppose you can suppose after this. If you do dimension 1/2, it's dimension 1/3, and so on. D'accord? Then I try another kind of model. Let's simulate now. We submit these papers almost to accept now. Because you have a lot of idea how to transform the 0-1 problem in linear programming, nonlinear quadratic programming, and so on. And this kind, if you suppose the objective function, so I call this WPQ, this VPQ. This, if you remember, are part of the objective functions, okay? And then look at that. I try to minimize these something, but I suppose this I can say what's mean. If YPQ is 1, if I minimize, you get you tie here. Here, if it's 0, that means the greater 1 minus 1 that don't care about the solution. Then you can work with VQ in this kind of optimization. This says I try to put this I can work like that. Of course, this is not very interesting, but it's a kind of model because what means now if I put that my formulation by formulation I have in this sense I can think this formulation here. That means I transform my problem in the sense here will be the model will be something like that. I keep all the 0-1 constants you see before 2 to 8, and I try to minimize the linear function, but here is no linear, but it's convex one. This means my relaxation now, perhaps I can do something with this. This means I have my problem now, this is convex problem, you see, but it's not differentiable in a sense. This is the second model, but it's associated with the first one, okay? This idea, and you have you solve this problem using what means the Bomlin problem and so on. 4 minutes. Oh, sorry. Oh. Okay. Then, okay. Look at just we saw, but that's very nice because Leo helped me.
These are the new models. These are still the.
But people never see that. You saw it, but that means that's a big problem. We arrived in this kind of function here, okay? On the lambda, I have to be differentiable. We try to put lambda 2 here. Then I found exact for 10 minus 8, and here for 10 minus 6, I find this one. It's not the same one. Because if you use this one, you find this solution. If you use a solution, here is very nice, but it's not the auto solution. Auto solution is this one. Just to see. Okay, then I have some tests here with this solution. Don't care. You get the solution. You get this octahedron for the dodecahedron for 3 hours. Sorry, for the cube 3 hours to solve. Not solve. This is the auto solution, but you cannot prove. and here is icosahedron, but that's just not very important. I have just to go directly. Then we try now to have some different way. The first one is work with the quadratic of this function. Here, like this. That's exactly model. You can use this kind of model. That's exactly. And you can write like that. It's very easy. And you can solve it. But that's the same promise. From this model, you can solve. You can have another kind of means decomposition of the solution and so on. Then have this one. Just to you have this one. And again, another one using, for instance, here I can use the distance, this distance here, and so on. Then you have all the relaxation here. Okay, that's the idea, principal idea. I change the function, the objective function, and all have to be less or equal to the given one. Okay, and here I lead these things, one of the, and I prove that's true. And I can solve the quadratic. Here is continuous, okay? And I can prove the first one, for instance. And I have this kind of possibilities and so on, just to show, but I'm sure there's different way, okay? That's with the infinite normal. It's good because it's linear in the sense. It will be linear, this one. And the bound is better than the quadratic one. Okay, the bound is here. You can see the bound here. Okay, the bound. This one is better than this one, and so on, and you go there, and here the same thing. Okay, then what I try now, some instance. Okay, that are the instance we try tetrahedral, octahedral, cube, icosahedral, dodecahedral, dimension of the simplex, and so on, and use this kind of logical simplex for the linear, and for nonlinear is kinetro. And we'll solve 2-3 hours. I don't think so. And here you cannot see anything, but I can see, but I don't think so. We test the 6 different relaxation, and just you understand, this is the best. Here is the best solution you can get. Here is the lower bound. Here is the solution I got in lower bound. I calculated the distance, the Euclidean distance of the solution. Okay, then I have this one. And this one here, a difference between this one and the better solution I have. That means you have very good upper bound in the lower bound, but the very large, the difference between the lower bound and the upper bound. But here, for this one here, the R4, I think so, you have the bound is better in this sense, okay? And you have very interesting because the solution here, this one, yes, is larger than the other ones, okay? This one is the same one, 0.5, 0.1, you see? But the solution is best, lower bound is here. But the solution I got here, using the infinite distance, give not bad, is larger than this one you get here. That solution, I got the solution here for the lower bound. I'll calculate now, this is not the infinite distance, but you calculated the Euclidean distance for the solution, okay? Because it's 3 and so on, but the solution is very bad when compared to the optimal solution here. That is much better the lower bound, but the upper bound, I prefer the other one. That's interesting because sorry, I think I have to do something. And then there's some idea we solve the solution for 8 is okay. For this is not optimal solution. We have the solution R2 and so on. It's solution solved by the relaxation, okay? And you correct the position, that's it. Okay. Thank you.
I think we have time for 1 or 2 questions. Yes?
If you use the square of the distance instead of the distance, is it always true that you need one Steiner point?
No.
And asymptotic is not?
No, because I put equal 3. You know the constants is equal 3. And I find exactly the solution, not the distance, you see? But the position is okay.
But the square of the distance doesn't make the problem much easier.
Yeah, exactly, but 0, 1. Much easier by 0, 1. The best to do is much easier is in the sense by the normal infinite normal, because you can write in linear, interlinear program, because the constants are 0, 1. That's big. It's mixed one problem, you know. In this case, linear or non-linear, that depends what you use. The idea is very, because the first time you can see some idea how to solve these problems for large one. Because I have a lot of idea of trick to find how to pound the things in and so on. I like it. It's kind of distant geometry, Euclidean distant geometry.
I think we have time for another question.
For 20 years I'm working this, but I cannot have no solution.
Listen, you went a little fast, so I couldn't understand these 6x4 relaxations or formulations that you worked on with Arsene. So what was the point of all that? Did you try a lot of combinations of the cost in the objective and then the cost in the constraints and then the cost here and the cost there? This is what you did?
Yeah.
It's like a sort of an exhaustive exploration.
But we proved that we have 6. 5 are the same thing, same solution.
Ah, okay.
The values, but the solution they got.
All right.
Okay? The best solution we got for the lower bound is very bound for upper bound. Very bad upper bound.
Okay.
It's interesting
So
because
there was one that was different in behavior?
of course the solution are not the same one for each one, but because the big problem when you test with this kind of polyhedron have a lot of symmetries.
Yes.
For the cube, have 12 solutions.
Okay, so if there was symmetry, the fact that the solutions may be different doesn't really matter.
Yes, but
It's the cost element.
what means you cannot eliminate when to do the branching bound and so on like.
Okay, there are some techniques maybe you should look into that.
Not easy. It's not just you have how to repeat the same configuration. Not very easy.
Okay, so let's thank the speaker again.